Hi guys, let's take a look at three problems in section 4.4. This is problems 1, 14, and 16. The first problem is just going to give you a graph, and then it's going to ask you information about the original function, the first and second derivative. So in a problem like this, you're just going to have to understand how the derivative works. So in my problem, I was given a quadratic that had a maximum at x is equal to 1. And so I automatically knew that the graph of the derivative, since this is a negative x squared function, it's going to be a negative linear function, in this case negative 2x, and it would have a positive y-intercept. The way I know that is because we know that the x-intercept has to be when the original function flattens off at x equals 1. So my derivative has to have an x-intercept at 1, and then it has to be positive before that because the slope of this equation is positive, and then it has to be negative after that x-intercept because the slope of this equation is negative after it. So it's just connecting the graph of the original function with its derivative, and then with its second derivative, I can say, well, the second derivative is just the derivative of the first derivative. And if I know that my first derivative is linear, then its derivative is just going to be the slope. In this case, it's going to be y equals negative 2. I was thinking this is negative x squared, so the derivative of negative 2x, second derivative negative 2. And that should make sense in the context of the original function as well, because we can say that anytime the second derivative is negative, the original function is concave down. This original function is always concave down, which is why the second derivative is always negative. Now, in a case like this, the problem is going to be asking which is less than, and I could say, well, at x equals 1, clearly the second derivative evaluated at 1 would be less than the first derivative evaluated at 1, which in turn would be less than the original function evaluated at 1. So you would just select the option on achieve that has that set up right there in a problem like this. It's a great problem. Love that one. The second one is asking you to do the second derivative test, and it's wanting you to do the second derivative test not only to determine intervals of concavity, but also to determine whether the critical points are maxima or minima. So let's talk about how to do that. We have a rational function given, in this case x over x squared plus 21. Make note that the domain of this rational function, we know that that domain is all real numbers, so negative infinity to infinity. There's no value of x that's going to cause that denominator to not exist. So then I can go in and say, well, with the understanding that that domain is all real numbers, I can go ahead and take the critical points and the inflection points and know that nothing needs to be restricted. Taking our first derivative, I bring the denominator up to the numerator times the derivative of the numerator, 1, minus the numerator times the derivative of the denominator, 2x, all over that denominator squared. So then I just need to simplify that expression, and I knew that I would have an x squared minus a 2x squared for negative x squared. Then I have plus 21. We know that the critical points occur when this first derivative is equal to 0. The only way a fraction can ever equal 0 is if the numerator of that fraction is equal to 0. So I can say, well, then 21 is equal to x squared, which is then going to give me x is equal to the positive negative square root of 21. So now I can say, all right, I have my critical points. I'm not worried about whether those are maxima or minima. My second derivative test will tell me that. So I go ahead and take the second derivative. In my second derivative now, I can say, well, I'm taking the derivative of the first derivative, so that denominator comes up to the numerator, times the derivative of the numerator, the negative 2x, minus the numerator times the derivative of the denominator, and I had to use the chain rule on that. 2 came down in front of the group x squared plus 21 to the first power times the derivative of the inside, 2x. Now it's important that you simplify these in a nice manner, or in an effective manner I should say, in order to be able to set the second derivative equal to 0. So whenever I'm doing that, I'm thinking, well, please notice in your numerator you have an x squared plus 21 here an x squared plus 21 here, you could factor out 1 power of x squared plus 21 and cancel it with one of the powers of x squared plus 21 in the denominator. That's why I just have x squared plus 21 cubed in the denominator now in this step. My numerator is going to be negative 2x times x squared plus 21 to the first power. And then I would have minus, I said 2 times 2x is 4x. And I still have this group negative x squared plus 21. So now when I simplify, I would just go ahead and distribute and combine like terms. I'll have a negative 2x cubed plus a 4x cubed for positive 2x cubed. I would have a minus 42x, and then I'd have a minus 84x. That's going to combine to be a minus 126x, of course, over our denominator. Now, so the simplified version, all I did from this step to this step was I factored a 2x out of the numerator, greatest common factor. Now that I've done that, I can see that this fraction, the second derivative, can only equal 0 if the numerator is equal to 0. So I'll say the possible inflection points occur when 2x times x squared minus 63 is equal to 0. It's going to give you a potential inflection point at 0 and another, or two other ones, when x squared is equal to 63. If x squared is equal to 63, then x is equal to the positive and negative square root of 63. And then I said 63 has a perfect square factor of 9. I could call the root of 63 the root of 9 times the root of 7. We know the root of 9 can be simplified as 3. So now I have x is equal to 0 and positive negative 3 on the root of 7 as my critical points. So now I come in and I do my second derivative sign test. The second derivative sign test tells us to break up the domain of our original function, which was all real numbers, with these critical points. My leftmost critical point was negative 3 on the root of 7. So you'll see I went from negative infinity to negative 3 root of 7. Then I went from negative 3 root of 7 to my next, and I think I called it critical point. I meant potential inflection point. I go from negative 3 root of 7 up to my next potential inflection point of 0. Then I go from the potential inflection point of 0 up to the last one at 3 root of 7. Then I go from 3 root of 7 to infinity. Now, I know that 3 root of 7, positive, negative, it's very, very close to 8. The square root of 63, close to 8, you can say, well, root of 63 here, 7.94. So when I'm thinking, well, in this first interval, I need some value between negative infinity and negative 7.94. I chose a negative 10. I need some number between negative 7.94 and 0. I chose a negative 1. Some number between 0 and 7.94. I chose a 1. And some number between 7.94 and infinity, I chose a positive 10. Now again, nothing special about those test points other than they do lie within the region they're supposed to represent. Now, these test points get plugged into my simplified version of my second derivative. I know that denominator, no matter what I plug into it, it's a number squared plus 21 cubed. That's always a positive. So you'll notice the denominator of each of these expressions is positive irregardless of what you plug into it. But it's the term in the numerators that's going to determine the sign of the second derivative. So when I plug a negative 10 in, I'll have a negative times, the second term would be a positive because it would be 100 minus 63. Well, a negative times a positive divided by a positive, it's going to give us a negative there. Anytime your second derivative is negative, you know your original function is concave down. When I plug in the negative 1, the factor of 2x is still negative, but the factor of x squared minus 63 is also going to be negative now. So you'd say, well, your numerator is going to be a positive, therefore your fraction is a positive, and you can say your original function is concave up in this region. Then when I plug in a 1, the factor of 2x is positive, but the 1 squared minus 63 would be a negative. That's going to generate a negative fraction for the second derivative, and thus the original curve is concave down in that region. Lastly, when I plug in the 10, you can see every single factor would be positive. You'd have a positive 20 times a positive 37 over a positive denominator. We're positive that the second derivative is positive in that region. Whenever that's the case, your original function is concave up in that region. Now, the questions that they're going to ask are the intervals of concavity. So first of all, the intervals of concavity, this function is concave down from negative infinity to negative 3 on the root of 7, and it's concave down from 0 to positive 3 on the root of 7. So the way you would note that over here, you'd say concave, I'll say down to abbreviate. That's going to be from negative infinity up to negative 3 on the root of 7, and now achieve will want you to put the union in between. So this is union 0 to positive 3 root of 7. And then they will ask, when is this function concave up? Well, it's concave up whenever the second derivative is positive. And you would say, well, that's going to be from negative 3 on the root of 7 up to 0, union, and then the other portion where it's concave up, where the second derivative is positive, is going to be from 3 root of 7 up to infinity. The other questions they're going to ask are the critical points and where there is a maximum or a minimum. You could have done the first derivative test, but there's really no need to here. You can look at your critical points and see where they would lie within your second derivative test. So when I'm thinking positive, negative, square root of 21, well, the square root of 21, it's just 4.58. So the negative square root of 21 would be negative 4.58. I know that that's going to fall in this region right here between negative 7.94 and 0. So the critical point, that's the negative square root of 21. The only critical point that can lie within a region that's concave up has to be a minimum. So all I have to do is see where the critical point would lie in the second derivative test. If it falls within a region that's concave up, it has to be a minimum because the function's U-shaped in that region. If the critical point, such as the square root of 21, which would be 4.58, it's going to fall between these two numbers, well, that's in a portion of the graph that is concave down, has negative concavity. So you could say, well, then any critical point in that region has to be a maximum. So you would answer the questions for maximum and minimum. That has a maximum at the square root of 21 and has a minimum at the negative square root of 21. Pretty straightforward. The last one in this section that I'll look at with you, and it is literally the last problem in the section, number 16, very, very similar to the one we just looked at. It's a little bit better just because it involves the product of a polynomial and an exponential function, but it's the same type of questions. Determine the intervals of concavity, and then determine the critical points that will give you maximum or minimum values. Okay, so I know I'll have to take the second derivative. Let's go ahead and do the first derivative. Derivative of x squared minus 5, 2x, times the second, plus x squared minus 5 times the derivative of the second, which is e to the negative x, times the derivative of the exponent, negative 1. Now I can say, well, all right, at this point, when I went from here to here, I went ahead and I distributed this negative 1 throughout this group. And that gave me e to the negative x times negative x squared plus 5. That made it easier for me to factor out a common factor of e to the negative x here. And when I did, I said, well, if I factor out an e to the negative x, what polynomial is going to be left over? You'd be left with a negative x squared plus 2x plus 5. That's where this came from. Now I can go in and take the second derivative. Second derivative, derivative of the first term, negative e to the negative x, times the second, plus the first, now times the derivative of the second, which is going to be your negative 2x plus 2. So now when you get to this point and you say, well, I need to simplify, once again I would want you to factor out an e to the negative x, but when you do that you need to be careful about what's left over. If I factor out an e to the negative x here, this factor of negative 1 would still have to distribute through that polynomial, which is going to give you a positive x squared. That's where this came from. It would give you a minus 2x, but then you have another minus 2x. They combine to be minus 4x. It would also give you a minus 5. Minus 5 plus 2 combines to be minus 3. So now I have my first and second derivative in gorgeous factored format. Makes it easy to find my critical points and my possible inflection points. Critical points are where your first derivative is equal to 0. Exponential functions can never equal 0, but that quadratic one can. What I went ahead and did from this step to this step is I didn't like the negative in front of the x squared, so I just multiplied both sides of this equation by -1. 0 times -1, obviously still 0. But then I saw that this quadratic, it's still not going to factor. You can't find factors of -5 that sum to get to -2. So I just used the quadratic formula to solve out for when this is equal to 0. We said it's going to be +2 plus or minus the square root of b squared, 2 squared, minus 4 times a times c. That gave me minus a -20, which plus 20. Then I can say, well, all right, that's going to be the square root of 24. Square root of 24 simplifies down to the root of 4 times the root of 6. The root of 4 is going to simplify as a 2. So now I have 2 plus or minus 2 on the root of 6 over 2. I can go ahead and cancel out those 2's, and I don't know why I put the 1 in the denominator. It's not necessary, of course. It would have been better just to go ahead and say this is going to be 1 plus or minus the root of 6. And then 1 minus the root of 6, just to help me out as to where to place it in my second derivative test. 1 minus the root of 6 is the -1.449. 1 plus the root of 6 is the 3.449. Now, Achieve will want the exact answers, so the only reason I got those decimals is so I could think about where they fit when I did my second derivative test later. Now, similarly, I could find my potential inflection points by taking the second derivative equal to 0. Again, the exponential function cannot equal 0, but that quadratic can. I use the quadratic formula again. -b plus or minus the square root of b squared minus 4ac. Inside the square root, I'll be getting -4 squared is 16. Minus 4 times 1 times -3 gives me plus 12. All over 2a, well, that's 2. Now this time I have the square root of 28 there. I was thinking, well, square root of 28, that's just the root of 4 times the root of 7. That root of 4 would be a 2. That 2 can get factored out. So I would have 2 times the group, 2 plus or minus the root of 7 over 2. I canceled out those 2's and said, this simplifies to just be 2 plus or minus the root of 7. Now again, Achieve will want the exact answers, so these are the numbers I need to input into the platform and the answers, but it helps to think about what these are as decimals. 2 minus the root of 7, approximately -0.646. 2 plus the root of 7, approximately 4.646. So now, when I do the second derivative test down here, I'll say, okay, now let's think about our test intervals. The test intervals are the domain of this function, which is all real numbers, broken apart by your potential inflection points. That's the only time this function could change concavity. So we go from -infinity to the lower one, 2 minus the root of 7, the lower one to the higher one, 2 minus the root of 7 to 2 plus the root of 7, and then the high one, 2 plus the root of 7, all the way to infinity. These set up the test intervals for my second derivative test. I need to choose a point somewhere between -infinity and -0.646. I chose -1. Some number between -0.646 and 4.646. I chose 0. And some number between 4.646 and infinity. I chose 5. Nothing special about those other than they are within the region that they're supposed to represent. Now, notice, second derivative test every single time. You put your most simplified form of your second derivative, and our goal is to find out the sign of that second derivative in each of these regions. Now, automatically, the e to the -x, every single exponential function is always positive no matter what you plug into it. So that's an easy one. The only factor that's going to determine whether the second derivative is positive or negative, though, is this second one. When you plug a -1 into it, it would be +1 plus 4, so that's going to be 5. 5 minus 3 is a +2. Product of two positives, my second derivative is positive here, which means the original function is concave up in that region. And then when I plug in the 0, clearly that second factor is a -3, which means your second derivative is going to have a negative sign in that region, which means your original function is concave down in that region. And then finally, when I plug in a 5, the second factor would be 25 minus 20 minus 3, so 25 minus 3 would be a positive 2. Product of two positive numbers is positive. So I know that my second derivative is positive in this region, which means my function is concave up. Now, the questions that they will ask you on here is when, what intervals of concavity, when is this function going to be concave up? You simply say, well, it's the first and third region because that's where the second derivative was positive. So it'd go from negative infinity up to 2 minus the root of 7, and they do want the exact values, union 2 plus the root of 7 all the way up to infinity. When is this function concave down? Well, in the middle region. So that's from 2 minus the root of 7 up to 2 plus the root of 7. The other thing that they'll ask in addition to the intervals of concavity, they'll want you to go back and reference your critical point. So it's this 1 plus or minus the root of 6, and it's better not to have the 1 in the denominator. It's okay to have it, better not to. So the 1 plus or minus the root of 6, I can say, well, if I think about the negative 1.449, that's the 1 minus the root of 6, negative 1.449 would fall between negative infinity and the negative 0.646. So 2 minus the root of 7 is further to the right than this one, so that 1 minus the root of 6 falls in this first region. What do I know about any critical point that falls within this first region that's concave up? It has to be a minimum. This function will have a minimum when x is 1 minus the root of 6. This function will have a maximum when x is 1 plus the root of 6, because 1 plus the root of 6 is approximately 3.4. And you know that that's going to fit right in this middle region because the middle region continues until x is 4.6. So 3.4 or 1 plus the root of 6 to be exact would be the location of my maximum in this case. All right, guys, so hopefully this helped you out with these three problems here in 4.4. The 1, the 14, and the 16, they're all beautiful problems. Please let me know if you have any questions. Be glad to help.